Good morning. Good morning. Thank you. Little bit of life is always good in the morning. Uh, Helps me. Probably what I'll say is, inspires me. Now, look here. We've been looking a lot at earthquakes. I'll again continue to start my recapitulation with this four things. Okay. First thing is prevention. Is there any way by which I can prevent the damage? And if suppose I'm able to be prepared, it means that I'm in a position to mitigate the effect of it. Later on, I'm also going to see if suppose I can. I want to see how I respond to the earthquake. In a sense, am I going to be having a behavior which will cause more damage, or will my behavior help me to mitigate the effects of the catastrophe which has happened? And the last of which is how we recover from a disaster. In the last class, we saw how the strong motion plots, what you get from a seismogram, is reduced, and instead of using acceleration, we use a term called spectral acceleration. Okay, because we are having a collection. Usually spectrum is a collection. Okay, if you see, the visible light is what we see off light is what we call as the visible spectrum, what we put as the VIBGYOR. Same way here, what we do, we take the collection of frequencies which are going to be harmful to the structure, or what we perceive to be harmful to the structure, and then we do it. So we also saw that strong motions affect the strong motions of the earth essentially causes displacement. This causes inertial forces to be generated, and the dynamics of the system is such that there is always a stiffness in it, there is also damping in it, and all these parameters put together give a response of the structure. In other words, how it accelerates, how it displaces, okay, so on and so forth. What is the velocity which will get induced because of a displacement? Okay, and finally we saw something about the geometrical irregularities. We saw the irregularities in plan and elevation of the structure, and we feel and we are stating that it is better to have what we call as a configuration which will not accentuate the earthquakes. But it doesn't mean that we say that we cannot have a fancy structure. We even had a structure which was in the shape of an L, very large cantilever, very large overhang, very large eccentric overhang. It is still possible. However, design has to take care of the same. We went one step further. We saw what ductile detailing was. Ductile detailing is where we are able to give concrete, which is essentially a brittle material, the ability to bend more. Same thing occurs to steel. It depends on how you make the connections. If you make a connection which can deflect and still be what we call as integral, that means it's a very good type of detailing which we have done. Detailing is nothing but how we give, for example, the various elements which take care of the load. Okay, and yeah, that's what was ductile detailing. I'll add one more point to you guys. The forces which come on the structure is either a compression which pushes each of the elements close to each other. For example, if the masonry elements are going to have a vertical compression, it's going to take it very nicely. However, if suppose I'm going to slide it, the blocks can all slide one on top of the other. One layer can slide over the other and fail. Okay, so this is the sliding type of failure is called shear failure. Okay, so these were basically what we've been seeing till now. Now look at the beam column junction which we have over here. Now if you look at this first column, can you see the concrete has got crushed locally, and when the concrete also fails, it starts to push the reinforcement rods outside, and there are no links. Okay, whatever is the thing which is put in the other direction is totally absent. This makes the structure very vulnerable to damage. Okay, again look at this area. Again, this is the link I'm talking about. Okay, this particular failure is what we call as delamination. The outer part has come out, but in any case, that is because it has bulged. The plaster, whatever was on top, has been pushed away. That's basically what has happened. So essentially what we are trying to put across to you is that we don't like the concrete to bulge out. We don't want the concrete to bulge out, and this is why if you see the new codes ask us to provide very large amount of links at this junction. Okay, so typically if I'm going to go and tell a person that please provide more number of links in the beam column junction, they'll say they'll ask the mason, "Arey, I've built so many structures all around, look, is any of them having any problem?" The problem comes when an earthquake is going to hit your city. It is going to be the difference whether your building is going to be usable after the earthquake. See, most of the concrete buildings need not collapse so rapidly. But suppose you see the building is intact, but if suppose this particular portion is alone failed, are you going to be happy to live in that building? And it is your building many times which you are doing the taking the decision. Okay, so at this point of time, if you ask me, at the beginning the cost is slightly more, but after an incident your structure is still usable. Okay, so this is something which you please think about seriously. Okay, the joints have to be detailed properly. In the last class we told the reinforcement rod has to go deep into the concrete to a length what we call as the development length. If you don't put it deep enough, it is going to come out in the event of a pulling action, and reinforcement steel is only for tension. Okay, now let us go a little further. So you can see the cracks here are having a diagonal pattern. The cracks in the beam are having a 45-degree pattern. These are shear failures. Essentially, suppose I am looking at this, had this been a beam, it's very deep, and it means that it has not been able to take the shear force. This is the depth of the beam. The span is very small. It is a very stiff element. Okay, and we'll ask ourselves a question. Typically, whenever an earthquake strikes a developed country, the loss of life is less. Why? Sorry? See, when you see recently there was this tragedy of people getting caught in a building on fire. Okay, what is happening? Typically, we overcrowd our cities. Our structures are not engineered. Okay, and it is very likely that we find a building fall on top of the persons. If this building had been engineered right, it is not going to fall on the person. You are going to be safe. Okay, now for the benefit of those who are sleeping, okay, let us all stand up. Okay, stretch and sit. I know those who are sleeping will find it very annoying, but yes, please stand up, stretch yourself, and then settle down. Yeah. Look at this. Usually the earthquake causes a cyclic motion. Okay, if you take a steel ruler and provide cyclic motion, that is, you are repeating the same motion, what happens to it? It undergoes a phenomenon called fatigue, which makes it fail even at a much lower force than what it could have taken. See, you take the same scale, keep on loading it for a very large loads, you will find that it takes a very large amount of force before it buckles and breaks. Okay, on the other hand, if you are continuously doing a cyclic motion, even though the load is very less, okay, I'm keeping a mass, I'm vibrating it, keeping on vibrating it, at a very low load itself it tends to fail. This is the problem with fatigue. Okay, so most of the times, always whenever there's an earthquake, you're going to have a cyclic load. So these slides show, especially where the staircase gets failed. Okay, and this is from a research paper which was studying how the earthquakes affect the staircases in particular. Okay, we've been talking a lot about beams, columns. Okay, why are we focusing now on staircases? Suppose you are on the 15th floor, right? What is the best way to come down when there is an earthquake, right? And you'll find that many times the staircase alone fails in a building, leaving a person stranded, or where you are going to have some thing where the staircase stands and the rest of the building fails. That also we have pictures. But in any case, I just want to put that this is also one of the very important things which we need to consider. Okay, I am going to introduce to you a new concept called base isolation. Not new, It's a concept which has been there for a very long time, but we have not introduced it in our class. First thing we did was we tried to see whether the frame, structural frame itself is strong enough to take the earthquake forces. Second thing we saw, we can change the stiffness or the location of mass, and then we can cause a benefit, like where it reduces the effect of earthquake. Third thing is base isolation, where we don't allow the strong motion to reach the building itself. Okay. Now I kind of I should have probably told this a little earlier. There are many ways by which you can strengthen the columns. Okay, for example, you can give additional reinforcement, some additional steel plates, or you can wrap the column itself with fibers and then make it stronger. Essentially, you don't want the whole thing to spall out. Okay, so this is for making a structure stronger. Okay, and earthquake today, like all the studies, all the results we got are from a lot of studies which people have done on walls, on almost full scale models. And if suppose your structure is not going, if you feel your structure is not going to perform well in an earthquake, these are some of the ways additional load paths are given so that you can ensure that all the horizontal motion reaches the ground. Okay, so yeah, your structure is not safe, fine, not a problem, there are solutions for it. Okay, so these are some of the retrofitting which has been done. Now this is the base isolation. This is the conventional structure which deflects more at the top and much lesser at the bottom, and the force gets transmitted and affects all the structural elements. The second one is where we are having base isolation. Again, base isolation is something which is designed. Okay, you need to see what is the frequency of the building, what is the type of excitation which is going to hit the building, and then you decide the base isolation. Lots of types of base isolators are there. So I'm just introducing one kind to you. Look at this. These are some bearings which we have kept. This bearing allows the ground to move without allowing the forces to uh, reach the structure above. Okay. Uh, Now to give you an idea of how effective these materials are, if you see the railway track, on top of the concrete sleeper you will see that there's a very small pad. There's a neoprene pad which has been kept, and that is sufficient to take care of a lot of impact which the train is going to give on the sleeper. So you can imagine that's what materials are there. I mean, material science has grown to that level that we are able to engineer materials of various types. Okay, so this is an example of a base isolator. The other exciting thing is tuned mass damper. What happens is, suppose the structure is going to have a particular frequency. Suppose I'm going to have something which will give the opposite frequency. Okay, opposite, it will be in the opposite direction of motion. It is effectively going to nullify whatever is the movement. Okay, so this is a tuned mass damper. Here are some examples of the tuned mass damper. Nothing but a huge mass kept on top of the skyscraper. Okay, so basically the one below is the dynamics calculations of it. Mass of the building, the tuned mass is kept on top. You can adjust the dashpot. Viscous dashpot is the one. This is the second part. What we have, the F2 term is essentially the dampers parameter. The other one, K, is the stiffness of the system. Okay, so in choosing the damper, if you are able to choose it so that the majority of the the frequency is such that it is opposite, it will act in a direction opposite to that of the motion of the structure with the same frequency of the structure, you are going to have a damping effect. Okay, the structure is not going to vibrate to a very large extent. Okay. Essentially, it is like having one person move one side and the other person moving on the other side. If another child is kept on this table, a small vibration will be felt. That vibration is because one mass is larger than the other. Okay, but on the other hand, if I'm just out of sync of the other person, the amount of excitation is very less. On the other hand, both of us are in sync. Both are dancing with the same direction. Okay, that means the child is going to face is going to experience a lot of motion. Essentially, this is what a tuned mass damper does. This is the Millennium Bridge in London. They found that it was vibrating due to passengers when the pedestrians walk, it started to oscillate a lot. So what they did, they kept some dampers on it, so that it will absorb the displacements, the excitations caused by the people. This is one example, one more example which I thought I'll share it with you. And this is another exciting one. Okay, now this is a Stockbridge damper. This is a Stockbridge damper. You will see it on the high tension wires. When the wind flows past this wire, it causes a very low frequency oscillation. Suppose all the wires start to oscillate in phase, it will cause damage to the tower. Out of phase, they'll start to arc. Okay, so it's dangerous when all the cables sway together in the same frequency. It is dangerous when the cables sway in the opposite frequency. So what we do, we keep this damper on the top. Okay, and these clips, I mean, this is just like a clip. It's just fit on top. It protects the insulator string. It also protects the cables from snapping. We were talking about fatigue. So suppose it is the low frequency continuously what you call as oscillating, it is again going to cause damage to the cable or to the structure or to the insulator string. We don't want any of this to get damaged. Okay. Anybody from electrical school here? Select. Any guess what this is for? You've done this in physics of 11th or 12th. Action of points. Remember the thing, action of points? Okay, don't worry. This is nothing but where this is a two sharp points which we have. In the event of a lightning strike, then what happens is it is designed so that an arc is formed between these two things. Okay, I'm forgetting the name of what this protection system is. So the insulator will not fail. Okay, when very large voltage is applied, even the insulator can fail and it will start to behave like a conductor. So to protect the insulator, these points are kept. You can see it on top of the what you call as the locomotive also. You'll have some of these points kept across some of the insulators. Most of the switch gear has this. Okay, so in any case, in my class we are more bothered about these dampers. In the earlier days, they used to keep two concrete blocks on the cable. Now they are keeping steel. Okay, so this acts like a damper because it starts to vibrate. It vibrates in the opposite direction, and this is what we use in our structure also. Now this is tape 101. I don't know whether let's see if I can get my mouse to work first. Um, just a minute. Let me 101's what I call as the tuned mass damper which they have there. It essentially gets activated when wind blows on the structure. Also when there's an earthquake, it is going to do it. That particular video was during one of the gales which hit the building. Okay. Now the secondary effect of so till now what we have seen is we have seen an end-to-end package of what happens on earthquakes due to earthquakes. Earthquakes can strike the building. It transmits the forces to the structure by way of a base excitation. The entire structure responds to the earthquake. We can make the structure strong enough to take up the forces, or we can give it a way by which it doesn't respond to the earthquake. And also for that we've seen two things: the base isolation, and we saw the tuned mass damper. Now I'm going to just give a very brief introduction to this tsunami. Our earthquakes essentially is having a fault which displaces the water. Now at this point the depth of the ocean is very large. The place when it may be a few hundred meters or sometimes kilometers of depth. When this wave is having a very small displacement at that depth, the wave will not be visible on the surface of the earth. But as you know, like when you drop a pebble in the water, the standing wave moves to the bank of the lake. The same way, the ocean's water moves towards the seashore, and as it progressively comes close to land, the amount of space which it's having to undergo vertical displacement gets reduced. Okay, so this attacks your city, and this was some of the things, like, this was the tsunami we witnessed some time ago, and we may not have been very familiar with tsunamis, but for the fact that it hit our own country. Andamans and so many other places were very badly damaged. Recently, the Fukushima's reactor also got impacted. There was an earthquake. The earthquake caused a tsunami. The tsunami caused the power systems, the power generation systems to shut down. What is the time? Okay, it's now there are other ways by which the earthquakes can the tsunamis can strike. The other ways the tsunamis can strike are because of an underground volcanic eruption. Okay, earthquakes are also sometimes linked to volcanic activity, but in our case, if there's an undersea volcano and a volcano is erupting, we are going to have the generation of the waves. Okay, the other thing is, maybe there is a landslide and the water, the lot of sand or soil gets dumped on the lake. When this happens, just a minute here, guys, can I request you to please move away? Is it your class next? Yeah, what? When is your class set? Yeah, it's only 10:30, right? You guys are making too much of noise. Can you please move away? Okay. So now here what happens is, yeah. So if suppose there's a landslide and it goes into a lake, the water in the lake, or even the sea, can be disturbed greatly. It could also cause a tsunami. Or if you are having a meteorite come and strike, okay, and it causes it's like taking a very huge stone, throwing it in the middle of the water, and the standing wave which reaches the end is causing a tsunami. Okay, so basically now if you see, we have essentially tried to see what are the principles by which we are going to avoid the impact of a natural disaster. Okay, so we can prevent it, mitigate it, how we respond to it, and how we recover from it. These are the things which we are looking at. Again, we saw some of the geological aspects of earthquakes. Earthquakes are caused, I mean, in particular, now I'm moving straight to earthquakes. The principles, geological principles of earthquake is that uh, when there is an earthquake, you are typically finding that there is a plate movement. So we are looking at the surface of the earth. There's a plate motion because of the way the earth is made of. Okay, the layers move against each other, they strike each other, they compress or push against each other till they are not able to take it anymore. They either slide on top of each other, slip, or they have some relative motion. So they can form mountains, they can do other things, and one of the effects is also the cause of an earthquake. They can also cause an earthquake. Now when this earthquake is generated at the fault location, the energy gets radiated from that point as compression waves or primary waves. Secondary waves get set up due to the reflection, and also as it goes through various layers, it undergoes refraction. Light waves, when they go through your glasses, they refract. At least they go through my glasses, they refract. Or when they go through the lens inside your eye, they get bent. Okay, so this essentially causes a change in the original behavior of the shock wave. The shock wave that is presenting itself at the surface of the earth will be dependent on the layers through which it has moved, and also the layer on which the building is founded upon. Okay, so we cannot actually tell what exactly will be the nature of action. So we instead of taking a very specific value, only one value, we take a spectrum of collection or range, and then we put it. So now as far as seismology is concerned, you are only recording these strong motions. at various locations. So the earthquake which could be in the Indian Ocean will also be registered in America, Japan, and somewhere in Africa or Europe. So each of them will study these motions. They'll understand how powerful this earthquake was. They can interpret what is the source of this earthquake. So when they keep studying these plots, they try to predict the most likely location of the next earthquake. Okay, as of now we have reached a level to understand what are the effects of the earthquake very well. Okay, and the only problem now is we have not pinpointed the place where the earthquake will strike. So this is the problem, this is the only problem which we are still facing. And of course with the amount of what we call as the computing power which we are having, we don't know where this is also going to lead us to. Okay, so we are also, like, in my view, these principal elements and systems are the ways by which I can reduce the impact of these earthquakes. Okay, so any questions on what we have done till now, please? No questions? Okay, so with this we'll say that this module 3 is complete. Okay, and this was the that staircase, especially the one which I did, which I took the pictures of the staircase. It's from this research article. All the photographs were from Google, searching on after searching on Google. Some of them are not on what I call as the Creative Commons, but yeah, I'm using it hopefully that it is only for educational purpose. Okay, so thank you.